So a few days ago, I was casually enjoying my favorite calculus book with a cup of joe when I came across something completely unexpected and shocking. The hardest looking calculus problem I had ever seen. Wait, seriously? Here's where you can find it if you want to look it up on your own. I just had to try to solve it. But wait a minute, there was a hint. Can't look at that. So what kinds of problem-solving strategies should I use? My first thought was to use the tried and true strategy of solving a simpler problem. That 6,000 power was kind of scary. How about replacing it with, say, a 2? That should set off alarm bells in your mind that we might be able to use a trigonometric identity to solve this. In fact, that's one of the main themes of this video. Trigonometric identities are really useful problem-solving tools. The fact that the power is a 2 should remind you to use a Pythagorean identity. In fact, 1 plus tangent squared theta equals secant squared theta. Since secant theta is 1 over cosine theta by definition, 1 over secant squared theta can be replaced with cos squared theta. Technically speaking, this is only true when secant of theta is defined, which excludes odd multiples of pi over 2, but we're going to see that that's actually not a big deal. Now, to compute the integral of cos squared theta from 0 to pi over 2, it's easiest to use another trigonometric identity. I always teach this one to my calculus students. Cos squared theta equals 1/2 plus 1/2 cos 2 theta. That's the quickest way to do this integral. Maybe you even want to pause the video and finish it from here. An antiderivative of the integrand function is theta over 2 plus sine 2 theta over 4. You can double check this by differentiation. This needs to be evaluated from 0 to pi over 2. Doing so, in the end, gives us an answer of pi over 4. Take the time to double check this. Rest assured, I won't sing or hum anymore. I then followed the advice that I always give to my students and tried to understand this graphically. In fact, that's strategy number 3. Whenever you can, make a visual. I graphed 1 over 1 plus tangent squared theta from 0 to pi over 2 and saw that it seems reasonable for the area to be pi over 4. After all, if I made a straight line from the upper left corner of the graph to the lower right corner of the graph, I'd end up with a triangle whose area would be 1/2 times pi over 2 times 1, in other words, pi over 4, the same as the area under the red graph. It does look right by symmetry. Another way to think of this is that if I drew a horizontal line with a height of 1/2, I'd end up with a rectangle whose area is pi over 4. If I translated the origin to be at the intersection of the red and green graphs, it seems that the red graph would become an odd function. That might be really useful in solving the problem another way, and maybe even generalizing it. Though it would be important that the point of intersection is halfway between 0 and pi over 2. With regard to this example, it's worth zooming out to see that 1 over 1 plus tangent squared theta really does equal cosine squared theta, which is 1/2 plus 1/2 cos 2 theta, for all values of theta where our original function is defined. Again, technically that excludes odd multiples of pi over 2, but for the interval from 0 to pi over 2, that only matters at pi over 2, and in fact our original function has a removable discontinuity there, so it doesn't affect the value of the integral. I now had a strong suspicion that to do this integral would require a geometric approach. However, if we're going to prove anything, we still would have to do some symbol pushing. There may not be an antiderivative, but maybe we need to prove that some transformed version of this function is odd. Before doing that, I thought it would be good to try my hand at some more particular examples. The next simplest example I can think of is when the power of tangent theta is 1. In other words, how should we ultimately solve this integral by hand? It seems that there's no similar Pythagorean identity that might be helpful. In that case, it's best to go back to the definition of tangent theta. Tangent theta is sine of theta divided by cosine of theta, giving us an integrand with a compound fraction. To get rid of that fraction in the bottom, yet not change the function, multiply the top and the bottom of this fraction by cosine of theta. If we do it to both the top and the bottom, we're really multiplying by 1, and when we multiply it out on the bottom, the cosine of thetas cancel. In the end, the integrand simplifies to cos theta over cos theta plus sine theta. This is now the integral we have to do. Now, sometimes people will stare at something like this for a long time and not know what to do. And sometimes inspiration also comes by wishing the integrand was a little different than what it is. For example, if the numerator of this fraction was cos theta plus sine theta as well, it would be easy. The integrand function would be 1, and the answer would be theta plus c. On the other hand, if the original integrand had a numerator of cos theta minus sine theta, that would be easy as well. A substitution, u equals cos theta plus sine theta, would give du equals cos theta minus sine theta d theta. We would ultimately integrate 1 over u and get natural log of the absolute value of u plus c, and then we could make the replacement and get a final answer of natural log of the absolute value of cosine of theta plus sine theta plus c. But wait a minute, neither one of these is the integral that we want. However, they are related to it in a sneaky kind of way. Because of the common denominators, if you add these two integrands, you will get twice the original integrand. Therefore, the final answer will be 1/2 of this plus 1/2 of that, and effectively the c's can get merged into one plain old c. Here's the final answer for the indefinite integral. To do the problem at hand, convert it to a definite integral, use the fundamental theorem of calculus, plug in your numbers, evaluate, and you get the same answer as before, pi over 4. It's like magic. Once again, if we look at this graphically and draw a line segment from the upper left corner of the graph to the lower right corner of the graph, we get a triangle with the exact same area, and by symmetry, it does seem like our area is the same. We can also confirm this with a horizontal line and the area of a rectangle. And once again, if we translate the origin to the point of intersection of the red and green graphs, it does appear that the resulting red graph is an odd function. It seems like we've discovered a general fact. The power of the tangent may not matter. The answer might always be pi over 4. That brings up another strategy. Make conjectures and test them. For our problem, it probably would be quickest to use some technology to see if we're right. How about using Wolfram Alpha? For example, I can change the power of tangent to be 3. What do I get? The integral from 0 to pi over 2 is indeed pi over 4. And look, the graph appears odd when the origin is shifted to the point with coordinates pi over 4, 1/2. When I change the power of tangent to be 4, the same kind of thing happens. When I change it to be 5, the same. 6, the same. How about fractional powers? If I change it to be 3/2, I ultimately get the same thing. 1/2 is the same thing. Of course, it has to work if the power is 0, because that's integrating the constant function 1/2. We've done that before. You get the area of a rectangle with base pi over 2 and height 1/2, so the area is pi over 4. Could it even work with negative powers for the tangent? If I change the power to -1, once again we get an answer of pi over 4. The graph looks still odd if the origin was at the midpoint. However, now it's an increasing function instead of a decreasing function. Maybe this is related to the fact that tangent to the -1 power is cotangent. If we try to confirm it symbolically in the case where the power is -2, we start with tangent to the -2 of theta. That becomes cotangent squared of theta. 1 plus cotangent squared theta equals cosecant squared theta. 1 over cosecant squared theta becomes sine squared theta. This time as long as theta is not an integer multiple of pi, but that doesn't matter. Sine squared theta then gets replaced with 1/2 minus 1/2 cos 2 theta. This is now easy to integrate. You get theta over 2 minus sine 2 theta over 4 evaluated from 0 to pi over 2, and you get the exact same answer in the end. The details when the power of tangent is -1 are pretty similar to the case where the power is +1. The first initial difference is that cotangent theta is cos theta over sine theta instead of sine theta over cos theta. This results in needing to integrate sine theta over cos theta plus sine theta instead of cos theta over cos theta plus sine theta. We still use the same two facts as before, but instead of adding these integrals, we subtract them, canceling the cosines and giving a 2 sine theta on top. We've got to divide by 1/2 again to get this for the final antiderivative. The final calculations then look like this. We get the same answer, pi over 4, as always. Let's now test our conjecture symbolically. Let f of theta equal 1 over 1 plus tangent of theta to the p power for any power p. Translating the origin to the point pi over 4, 1/2 is equivalent to translating that point to the origin. This can be done through a couple transformations. Let g of theta equal f of theta plus pi over 4, which translates to the left by pi over 4 units, all minus 1/2, which translates down by 1/2 of a unit. Our claim is that g of theta is an odd function, and this should be helpful for integration. After all, when you integrate an odd function over an interval centered at the origin, you get 0. Our goal then is to prove the identity that g of negative theta equals negative g of theta for all possible values of theta. Besides needing trigonometric identities again, another strategy we'll use is to make use of algebra as necessary, possibly some kind of tricky algebra. Your algebra skills need to be good. Let's begin. Using the definition of g of theta, if we replace theta with negative theta, we get f of negative theta plus pi over 4 minus 1/2. Using the definition of f of theta, this becomes 1 over 1 plus tangent of pi over 4 minus theta all to the p power, then minus 1/2. Getting a common denominator that's the product of these two denominators gives us this expression. As before, pause the video and take time to double check this. Next, distribute the minus sign through the parentheses on top. 2 minus 1 is 1, and plus tangent becomes minus tangent. Now let's try to simplify negative g of theta. Using the definition, negative g of theta is negative f of theta plus pi over 4, then minus 1/2 becomes plus 1/2. Using the definition of f, we get this. Once again, getting a common denominator results in this, which simplifies to this expression. On the surface, it looks different than before. But with trigonometry, appearances can be very deceiving. Our new goal is to prove the identity that you see here. This is definitely not an obvious fact. For one thing, we haven't said what p is. P is an arbitrary real number. And even if you thought you could use the fact that tangent is an odd function, if you think about it, you'll quickly realize that doesn't seem to help much. Again, in large part because we don't know what p is. What we need is a sum and/or difference formula for the tangent function. Here it is. Tangent of alpha plus or minus beta is tangent of alpha plus or minus tangent of beta all over 1 minus or plus tangent of alpha times tangent of beta. Before going on, you might see if you can prove this on your own using similar identities for sine and cosine and the definition of tangent. To solve our problem, we want to use this formula with alpha equal to pi over 4 and beta replaced by theta. We will also want to use the fact that tangent of pi over 4 is 1 because sine of pi over 4 and cosine of pi over 4 are the same. They're both square root of 2 over 2. Here are the details. Tangent of pi over 4 plus or minus theta, again, using the fact that tangent of pi over 4 is 1, simplifies to 1 plus or minus tangent theta over 1 minus or plus tangent theta. The signs on the left and the right match in the numerator and are opposite in the denominator. This has a really interesting consequence. If we multiply tangent of pi over 4 minus theta with tangent of pi over 4 plus theta, we ultimately get two fractions that completely cancel to give us 1. In other words, we have the following two key identities. Tangent of pi over 4 minus theta is 1 divided by tangent of pi over 4 plus theta. These tangent values are reciprocals of each other, and if we raise both sides to the p power, where p is arbitrary, we get a similar kind of identity with the pth powers. That's because 1 to the pth power always equals 1. It doesn't matter what p is. Now let's apply the second of these identities. Let's go back to g of negative theta. In the first fraction that you see, involving tangent to the pth power of pi over 4 minus theta, replace both of those with 1 over tangent to the pth power of pi over 4 plus theta. After multiplying the top and the bottom of this fraction by tangent to the pth power of pi over 4 plus theta, and using the distributive property, we get cancellation, and we ultimately get an expression that equals negative g of theta. In other words, we've reached our goal. We've proved g of theta is an odd function. But how is this useful? It implies that the integral of g of theta from negative pi over 4 to positive pi over 4 is 0. This is an interval centered on 0, and g of theta is an odd function. Using the definition of g of theta, that means the integral from negative pi over 4 to positive pi over 4 of our original function, f, evaluated at theta plus pi over 4 minus 1/2 is 0. Properties of integrals means that the integral of f of theta plus pi over 4 over this interval equals the integral of 1/2 over the same interval, which is 1/2 times the length of the interval, which is pi over 4. Since our original integral was from 0 to pi over 2 of f of theta, effectively a change of variables gives us the final result. In this last line, to go between the middle two integrals, effectively we're replacing theta with theta plus pi over 4 and changing the interval from 0 to pi over 2 to negative pi over 4 to positive pi over 4. You should take the time to think about why this works. So this solves the problem in the general case, but is it the same as the book's approach? Maybe I should look at the book's hint now. The book's hint is to use a substitution. That's the section of the calculus book that it's in, to show that the integral we're interested in, with the particular power of 6,000, is equal to the corresponding integral with a cotangent replacing the tangent. Hey, wait a minute, that's the same as tangent to the negative 6,000 power. We've really already thought about that, though the author of the textbook doesn't know that. The rest of the hint is to then show that when you add these two integrals, you get the integral of the constant function 1 from 0 to pi over 2, which would equal pi over 2, and therefore our integral of interest I would equal pi over 4, just like before. So the sum of these two integrand functions should equal the constant function 1. And based on what we've seen before, it probably doesn't depend on the power. If we add 1 over 1 plus tangent to the p power of theta and 1 over 1 plus cotangent to the p power of theta, using the definition of tangent and cotangent, we get this. Simplifying these compound fractions gives this. And now you can see we're home free. There's a common denominator of cosine to the p power of theta plus sine to the p power of theta. We combine the numerators and then cancel to get the constant function 1. It doesn't matter what the power p is. But now we need to go back to the book's hint to use a substitution to show that the integrals I and j are equal. That seems a bit confusing. What kind of substitution would work? And would it work no matter what the power is? We can get insight into what to do by thinking about it graphically. Here we see the graph of 1 over 1 plus tangent of theta to the 2.5 power. We can transform it to 1 over 1 plus cotangent of theta to the 2.5 power by reducing the power of tangent down to negative 2.5. In doing so, we see that the original graph gets transformed to the new graph by essentially a reflection across the vertical line at pi over 4. I'll show the animation again. While doing so, take the time to notice that the point in the upper left at 0, 1 associates to a corresponding point in the upper right at pi over 2, 1. Something similar happens with a point in the lower right going to a point in the lower left, and a point in the middle, pi over 4, 1/2, stays where it is. This is a big hint that just maybe the substitution u equals pi over 2 minus theta might be what we need. After all, because of this equation, when theta is 0, u is pi over 2. When theta is pi over 2, u is 0, and when theta is pi over 4, u is also pi over 4. Keep in mind that this is equivalent to theta being pi over 2 minus u, and d theta equaling negative du. Now let's do the integral. Here again is the substitution. U equals pi over 2 minus theta. Theta gets replaced with pi over 2 minus u, and d theta gets replaced with negative du. Here is the resulting integral after that substitution. Notice the negative sign from the fact that d theta is negative du. Also notice the limits of integration have gotten switched around. That's because when theta is 0, u is pi over 2, and when theta is pi over 2, u is 0. But by properties of integrals, we can get rid of that negative sign if we switch the limits of integration around, giving us this integral. Now look at that integrand. In particular, the fact that we have tangent of pi over 2 minus u. Does that remind you of anything that we used earlier? I hope it reminds you of this identity. Tangent of alpha plus or minus beta is tangent of alpha plus or minus tangent of beta, all divided by 1 minus or plus tangent of alpha times tangent of beta. Now remember, our goal, based on the hint, is to not solve the integral directly, but to show it's related to a similar integral involving cotangent. So we should probably rewrite this in terms of cotangent. Tangent of a quantity is 1 over cotangent of that same quantity. Therefore, this equals 1 over cotangent of alpha plus or minus 1 over cotangent of beta, all divided by 1 minus or plus the fraction 1 over cotangent of alpha times cotangent of beta. We can algebraically simplify that by multiplying the top and the bottom by cotangent of alpha times cotangent of beta. In the end, we get this expression, cotangent of beta plus or minus cotangent of alpha, all divided by cotangent of alpha times cotangent of beta minus or plus 1. As always, take the time to double check this. We are about to use this identity where we replace alpha with pi over 2 and beta with u and use the minus sign version. Doing so gives that tangent of pi over 2 minus u equals cotangent of u minus cotangent of pi over 2, all divided by cotangent of pi over 2 times cotangent of u plus 1. Cotangent of pi over 2 is 0, and this then simplifies to cotangent of u. Because of that, our integral can be rewritten in this way, and that essentially finishes what we wanted to do. We have verified what the book's hint says to do, that I and j are equal, in fact, in an arbitrary power case. And again, we know that I plus j equals the integral of 1 over this interval, which equals pi over 2. Therefore, I itself, including in the arbitrary power case, equals pi over 4. Here are the full symbolic details if you want to pause the video and take the time to check it. So, was this the hardest calculus problem in the world? Probably not, though it wasn't easy. I did think it was pretty interesting, though. I hope you liked it. Thanks for watching.